Chapter 5.6 is Systems of Inequalities and Linear Programming. With systems of inequalities, we're back to having infinite solutions, which means we're back to a graphical solution. So let's start with just what it means to graph an inequality to start with and refresh our memory before we move to systems. So if I'm graphing an inequality, I'm going to just imagine that I'm graphing the equation. And notice this is a greater than or equal to. So half of the problem is actually when 4x plus 7y is equal to 28. So I'm going to graph this. This will be my boundary line. It's set up perfectly for the intercept method. So if x is 0, y is 4. And if y is 0, x is 7. Once I have 2 points, because this is a linear equation, I can just draw my, hopefully, straight line through those 2 points. We're going to imagine that that's a straight line. And then the only difference in graphing an inequality versus an equality is I'm not finished yet. I've got the or equal to part graphed. Now, if I didn't have the equal part, this would still be my boundary line. I would still go up to this line. I just wouldn't want to include it, and we would do that by drawing the line as a dotted line. But this one has the equal part, so it's part of my solution. I can include the values that make 4x plus 7y actually equal 28. And to determine the values that make 4x plus 7y greater than 28, I'm going to pick a point. Okay, I'm always going to pick the point 0, 0 if I can, because that makes my math very easy. This is the point where x is 0 and y is 0. So if I were to plug in a 0 for x and a 0 for y, then this is 0 plus 0 is 0 greater than 28. Since that's not true, 0 is not greater than 28, then don't shade the side with that point in it. That means I'm going to shade the other side of my equation. Had this been a true statement, I would want to include this point and shade the side that included the point. Okay, let's look at this next system. Oh, now I'm graphing a couple of parabolas, right? One has the equal, one does not. So this is going to be a solid curve. This will be a dotted curve. Okay, I got to refresh my memory about what I know about graphing parabolas so far. And I'm going to do this one in blue. I might want to factor that and recognize that that is really, I'm just going to imagine that I'm graphing the equation first, that factors as x plus 3 all squared. So I know if I'm graphing a parabola, my basic points are these. And if I were just graphing y equals x squared, I would connect these points, and there's my parabola. But I want to move every one of these points inside with the x, so go the opposite direction. I want to move them left 3. So I'm going to go left 3, left 3, 3, left 3, 1, 2, 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 3. And solid line. All right, solid line. So I'm going to connect these points with, hopefully, my parabola. I'm sorry, I can hardly draw on this tablet thing like this. And then I decide if I shade inside or outside. Again, I'm going to decide that by picking this point 0, 0 and plugging it in here. So with the greater than, right? So my question is 0 greater than 0 plus 0 plus 9? Is 0 greater than 9? No. So don't shade the region that has this point 0, 0 in it. I'm going to shade inside my parabola. Okay, now I'm going to graph this one. It's still a parabola, so I'm still going to use these same points. The only thing is that's reflected. So I'm going to take the negative of every point. Instead of y being positive 9, it's going to be at negative 9. And instead of y value being at positive 4, it's going to be negative 4. And then negative 1, 0. We've got that symmetry going here. Okay, this time I don't have the equal part, so when I draw my parabola in here, I need to draw it as a dotted curve because the points on this curve are not included in my solution. This time I cannot use this point 0, 0 because it's on my curve. So I'm going to do the next best thing and use the point 1, 1. So if I let y be 1 and x be 1, my question is 1 less than, remember this negative has nothing to do with that exponent. If it did, it would look like that, right? So is 1 less than negative 1? No, so don't shade outside. Again, I'm going to shade inside. And because this is a system, my answer would be where these two red and green shadings overlap, right? Those places would satisfy both inequalities at the same time. Because there is no overlap of my shading in these, this one is a no solution. My red and green shadings do not overlap. So nowhere are there any points that satisfy both of these quadratic inequalities at the same time. All right, let's try it again. We can have multiple 3, 4, 5 equations. So it's usually best to kind of keep up with your answer solution as you're going along. This one right here, recall how to graph that. That's saying x is in between negative 5 and 5. Note, it's going to be a dotted line. So negative 5, when x equals negative 5, that's the vertical line. X equals negative 5. And here's the vertical line, x equals 5. Okay, and I'm going to shade in between, right? Shading in between. So everything in between these two dotted lines is what I'm going to keep up with for my solution set. Okay. This is just, I'm going to imagine the equation, y equals negative 3. Well, just like these were vertical lines because there's only an x, this is a horizontal line because it's only a y. So y equals negative 3 is right across here. But again, it's really a strictly less than. It doesn't have the equal part, so I'm going to make it a dotted line. Okay, and less than No, it's a greater than. Y is greater than means I would shade everything above the line. So far, if these were my only two equations, this part and this box right here that's got red and green shading in it, I would go back and completely shade that in. That's my solution to these two. I've got one more equation to deal with, however. So let's look at that equation. Okay, it's set up again for the intercept method, but notice if x is 0, y is 0, and I only get 1 point. So I can either solve this for y or just find another couple of points. I know, what about 2 minus 2? 3 minus 3. As long as x and y are the same value, it's going to equal 0. So I've got this point 1, 1, 2, 2, 3, 3. Again, a dotted line because it doesn't have the equal to part. So I'm just going to draw a dotted line. Did I get off? And then I've got to decide where to shade. Okay, I can't plug in 0, 0 or 1, 1 or 2, 2 again to make it easy. So let's try to make it easy as we can. How about the point 0, 1? Remember, x is 0 and y is 1. So is 0 minus 1 greater than 0? Is negative 1 greater than 0? No. So don't shade on this side of the line. Shade on this side of the line. And again, my solution is the part where everything, all the shading overlaps. It's where I've got green and red and orange shading. So don't leave your answers looking like this. Right? You've got to go back in and completely shade in the region of your answer. Make it obvious what you're saying your answer region is. Okay, and this heavily shaded region is called the region of feasible solutions. The region of feasible solutions. It means any point in here is a solution to this system, right? It satisfies the system, so it's feasible. It's possible for that to be a solution. However, usually we don't just want any solution that's possible. We want our optimum solution, the best solution, right? Depending on what our equation is dealing with. If it's dealing with profit, we want the maximum solution. If it's dealing with cost, we want the minimum solution. So those things we can find out with something called linear programming. Linear programming is used to find the optimum value of a system of inequalities. If an optimal value for a linear programming problem exists, it turns out it occurs at one of the corner points of the region of feasible solutions. So our first step is just to graph. Well, we've got to pull out our constraints and graph those, find the region of feasible solutions, and then I'm going to take my objective function, the function I'm trying to maximize or minimize the function I'm trying to optimize, and plug in all the corner points. All right, so let's try one. How about this one? Robin takes multivitamins each day. She wants at least 16 units of vitamin A, at least 5 units of vitamin B1, and at least 20 units of vitamin C. Capsules, costing 10 cents each, contain 8 units of A, 1 of B, and 2 of C. Chewable tablets, costing 20 cents each, contain 2 units of A, 1 of B, and 7 of C. How many of each should she take each day to minimize her cost and yet fulfill her daily requirements? There's what I'm trying to optimize, right? Whatever I'm trying to either minimize or maximize, either one. Yeah, I want to minimize her cost. So for right now, I'm not concerned with the cost. First, I want to find my region of feasible solutions, and then I'll test those to minimize her cost. So I could do something like, say, let's let X equal, capsules, and Y equal tablets. I could do that. Or I could just say, let's use C and T, right? So that's what I'm going to do. All right, so I know that the cost is my optimization function. My constraints, or the restrictions then, are her vitamins. So I need to pull out an equation on her constraints, the restrictions. And she wants at least 16 units of vitamin A. Well, the capsules have 8 units of A. So 8 capsules, right? Every capsule she's going to take, she's going to get 8 units of A. Plus, the tablets have 2 units of A. So 2 tablets, that has to be at least 16. So at the minimum, 16. This has to be greater than or equal 16. This is at least 16. It could be more, but minimal 16. There's one constraint. Okay, I'm going to do the same thing for B and C. Okay, let's see. A capsule has 1 B. So she gets 1, if she takes 1 capsule, she gets 1 unit of B. And a tablet also has 1 B. But she needs at least 5 units of B. Okay. The capsules contain 2 C. So 2 capsules plus the tablets contain 7 C plus 7 tablets is the amount of C she's going to consume. And that needs to be at least 20. So greater than or equal to 20. Now don't forget, it also means that you can't take a negative number of capsules or tablets. So we have a couple of obvious constraints to add, that C has to be greater than 0, and of course T has to be greater than 0. Which means if I go ahead and graph these over here, that means I'm working in this positive quadrant right here, right? So I'm already confined to this quadrant, everything in there. Okay. So I might also want to keep up with which equation I'm graphing over here. Okay, and let's see, I'm going to go to at least 10 here, 8, so I'm good there. I don't need to change my scale, but I might need to look at that also. Okay, again, these are set up perfectly for the intercept method. If C is 0, then that means T must be 8. Okay, and I'll just keep up with them like this. this, I'm going to do this one in red. If T is 0, then C must be 2. Okay, if I try 0, 0, is 0 greater than 16? No, so I'm shading this side, right? This side. Okay, for this one, if C is 0, T has to be 5. If T is 0, C has to be 5. And if I plug in 0, 0 as a test point, is 0 bigger than 5? No. So I'm shading this side. Okay. For this one, if C is 0, T is 20 divided by 7, right? Or 2 6/7. Let's see, T is 2 6/7. And if T is 0, C is 10. Once again, 0 is not greater than 20, so I'm shading this side. All right, to go back and find my region of feasible solutions, right, it's going to be where I've colored green, red, and orange. It's everywhere. In this region. Okay. So anything in here is feasible. She can take 4 capsules and 7 tablets and get the vitamins she wants. She can take 8 capsules and 4 tablets and get the vitamins she needs. But she wants to get the vitamins she needs at the best price. Okay, so now I'm going to come up with her cost function, right? And the capsules cost 10 cents each. So 10 cents times a capsule. And the tablets cost 20 cents each. And I'm going to make a table, and I'm going to check every corner, because the minimum or maximum will be at our corner. Now, we've got kind of a mess over here. Let me go in and see if I can find our corners. All right, here's one corner. All right, so this is at 0, 8. All right, here's one corner. This is at 10, 0. And then here's a corner, and here's a corner. So I need to know the coordinates of these points. This one looks like it's 1, 4. Okay, and notice what it is. It's where the green line and the red line intersect. Let's see. Oh, I didn't do my colors over here. Let's see if we can go back and figure them out right quick. My green line was second, and so the orange line. You need to keep up with which one you have. Okay, you may want to number them, you know, line 1, put it over here, line 2, put it over here. But where my green and orange intersect, let's see if 1, 4 satisfies those equations. Yes, 1 plus 4 equals 5. And, oh, no, 1, 4 doesn't work right here, so that's not really the point 1, 4. I just couldn't draw a straight line, right? So how could I find out this intersection point between these two? Oh wait, it's my green line and my red line that's intersecting there. So let's try 1, 4 again. Ah, that works. 1, 4. So this is the point 1, 4. But again, what if we plugged it in and it didn't work? All I have to do are take these two equations and solve them, right? I would use, on this one, I'd use my elimination method, multiply by -2. I'd have 8c plus 2t equals 16. Multiplying by -2, -2c minus 2t equals -10. And I would come up with 6c eliminated equals 6. So c is 1. And if I know c is 1, I can find out t. Okay. Now this point. This is the point where my orange line and green line intersect. It looks like it's 3, 2. So let's go over here and see if that works in orange and green. 3 plus 2 is 5. That works. 3 times 2 is 6 plus 14. That works. That one is the point 3, 2. I'm going to switch colors when I go over back to my chart just so we can see these better again. All right, so these 4 points, 0, 8, 1, 4, 3, 2, and 10, 0 are my possible optimal solutions. I'm just going to plug them in up here. Right? Pay attention to which one's C and T. I put them all in an ordered pair, and I've got my C first here. So this would be 0.1 times 0 plus 0.2 times 8, which is 1.6. Okay, this would be 0.1 times 1 plus 0.2 times 4, which would be 0.1, 0.8, 0.9. This would be 0.1 times 3 plus 0.2 times 2, so 0.3 plus 0.4, 0.7. And this would be 0.1 times 10 plus 0.2 times 0, or 1. Okay, so that means if she buys 0 capsules and 8 tablets, she gets her requirements of vitamins, but it's going to cost her $1.60. 1 capsule and 4 tablets will also get her vitamin requirements, but cost 90 cents. Right here is her minimum cost. So don't forget to actually answer the question. How many of each should she take? She should take 3 capsules, 3 capsules and 2 tablets. That's answering one question. Okay. Should she take each to minimize her costs and yet fulfill her daily requirements? Actually, that's the only question this one asks. But be aware, sometimes it'll also ask, what is her minimum cost? So if it asks that, her minimum cost would be 70 cents per day. Right? 70 cents per day. Linear programming problems. I know this looks like a big mess over here, so that's why I say keep up as you go along with your section of region you're interested in. Okay. We'll see you next time.